Alright, welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are basically going to continue from episode 2, right? So with episode 2, we are going to look at types of sets that is going to include finite and infinite sets, right? We are still under the big umbrella union and intersection of sets, right? So before we dive deep into finite and infinite sets, we are going to look at some basic terms before we continue, right? So the first term we are going to look at is empty sets, or what we call null sets, null set. Now, when we talk about a null set or empty set, what does it mean, right? So we are going to look at the definition. We are going to look at the definition. Right? So a set is said to be null or empty when it has no elements, right? When it consists of no elements, right? So a set that contains no elements is called empty or null sets. Right. So the underlined word is no elements, right? It contains no elements, and that is what we call empty or null sets. Empty or null sets, right? So once you understood what an empty or null set is, now we can proceed to look at some notations, right, under the null or empty set, right? So some notations, right? So if you see phi, this is when it comes to sets, right? When it comes to set theory, if you see phi, it means empty sets. It means empty set. Or if you see an open curly brackets and an open curly brackets and a closed curly bracket, then it is also means an empty or a null set. So these are the notations. It's either you use this or you use this, right? So this is an empty or null set, and this is also an empty or null set. Now, let's look at some important things that you have to know, right? So some important observations. One, the empty set is not zero, right? The empty set is not zero. So if you do this, open curly brackets and a closed curly bracket, and you put an element here, that is not an empty set. That is not an empty set. So the empty set is not what? Zero. If you have this is not what? Zero. This is an empty set. This is an empty set. Remember, zero is an element. Zero is an element. So if you come here and put zero here, it means that you have a set, not an empty set, not an empty set. So this is how you note an empty set, either using phi or using an open and a closed curly bracket. Now, the second observation is that zero is an element. Zero is an element, right? Zero is an element. The empty set has no elements. The empty set has no elements. Right. So as I said earlier, 0 is an element. When you talk about 0, 0 is an element, right? So if you come and put 0 here, this is no more an empty set, right? But if you are talking about an empty set, it's either you use this notation or use this notation. An open curly brackets and a closed curly bracket. Then you can talk about what? An empty set. Now, let's look at the third observation from these notations. The third observation is that you can see that phi is a subset of what? A, right? Phi is a subset of A for every set A, right? Phi is a subset of A for every set A. So if you take an empty set, every set that you pick, so let's say you pick A is a set of even numbers, or A is a set of odd numbers, an empty set is within that set, right? So that is the observation. An empty set is a subset of what? A. A is for every set what? A. So A can be any set. So it can be a set of even numbers. It can be a set of odd numbers. Anything, right? So an empty set is a subset of what? Every set, right? That is the third observation. Now, we have seen the clear observation from what? An empty set. Now, let's look at some few examples. Right? So we have first example is when you have a set of real solutions, right? So set of real solutions of, let's say, x squared plus 1 is equal to 0. X squared plus 1 is equal to 0. We are saying that this is an example of what? An empty or noun set. Why do we say that? This is an example of a noun or an empty set because it has no real solution, right? It has no real solution. If you try to make s the subject over here, you're going to have what? S equals what? -1. And if you take square root on both sides, you're going to have what? Square root of a negative value, right? And at this point, we are not interested in complex numbers. So it has no real solution. So it means that this is an empty set. S squared plus 1 equals 0 is an empty set, right? So we say that this has no real solution. No real solution, right? So this implies that it is an empty or noun set, right? So if you see this is an empty or noun set because it has no real solution. It has no real solution. Great. Now, example 2, we can talk about the set of even prime numbers, right? The set of even prime numbers less than 2. And in here, we know that even prime numbers less than 2 are 0 and 1, right? And 0 and 1 are not prime numbers, right? 0 and 1 are not prime numbers. So this is basically qualified to be what? An empty set, right? So this is an empty set because even prime numbers less than 2, that means we are limited to what? Only 0 and what? 1. Only 0 and what? 1. So this is what? An empty set. So that's an empty set. That's an empty set. Great. So now we have gotten two examples of what? An empty set. Now let's look at some exam traps, right? Exam traps that they can set for you or you can fall into. So we look at some exam traps. So you have to avoid this. You have to avoid where you do writing something like this and then you put 0 inside. This is not an empty set. So this is a trap. So if you see something like this, this is not an empty set. So don't try to write something like this as an empty set, or if you see something like this and they are saying that it is an empty set, cross it like this. This is not an empty set, right? This is not an empty set. So never write something like this and say that, no, this is an empty set. This is wrong. Two. All right. So instead of you writing this, you have to write phi or open and close curly bracket. So you don't write this. This is not correct. Write this or this. So this is an exam trap, and you have to know that the correct way is this or that. Now, we have been able to know the exam trap, and so we will not commit it when we are dealing with empty set. All right. So we have looked at the definition of an empty set. We have looked at the important observations. We have looked at some examples. We have looked at 2 examples, and we have looked at the exam trap. Now, the next thing on the list is singleton, right? Singleton. When we talk about singleton, how do you understand it? Leave your answer at the comment section. I'll give you some time to leave your answer at the comment section. Are you done? All right. So when we talk about singleton, the name itself defines the term, right? The name itself defines the term. So we talk about singleton sets, right? So we are going to look at the definition, then we look at some examples, then we move on, right? So when we talk about a singleton is basically a set that contains only one element, right? So we say that definition, a set, this is a set that contains exactly one element. That contains exactly one element, right? So that is what we call singleton set. So it's a set that contains exactly one element. Then we can talk about singleton set. Now, let's look at some examples of a singleton. So what we did here is basically an example of what? A singleton, right? So example is, let's say A is equal to open into 0, close curly bracket. So this is an example of what? A singleton. It has exactly one element, not more than one, exactly one element, and that is called a singleton set. This is not an empty set. This is not an empty set. And this is not an empty set. This is called singleton sets. All right, so the next thing that we have to look at is, we have to write it there boldly for you to remember that this is not an empty set. So this is not an empty set. So please take note of it. This is not an empty set. This is called singleton set. This is called singleton set. Now, once we have been able to adapt ourselves to empty and singleton sets, now let's look at the key differences between these two terms, right? Between these two terms. So, key differences, right? So we're going to look at some key differences. So we say that this part should be expression and this part should be the meaning, right? So if you see 0 here, all right, 0 here means a number, right? So a number. 0 is a number. Of course, it's an element, right? So 0 here means a number. Then if you see 0 in a curly bracket, that means a set with one element. A set with one element, right? So this is called a set with one element. And that is qualified to be a singleton, right? So this is the second difference. Now, the third difference is that we have empty set here, and then we have a set. The meaning is that a set with no elements. So we have 0 means a number. 0 in the curly bracket means a set with what? Only one element. An empty set, the symbol of an empty set or the notation of an empty set means a set with no element. And that is what? An empty set, right? So if you are okay with the differences, now we can go ahead and start with the main business for the day, right? So we are going to look at the main business of the day, which is the finite and infinite set. So we're going to begin with finite and infinite sets, right? That is the main business of the day. So we begin with the finite set. Finite sets. All right. So we have been learning this from high school to junior high school to senior high school. We have been talking about finite sets, infinite sets, set. We know about set, right? So what we are just going to do, we are just going to make sure that we strengthen our understanding in those concepts, right? At some point at that level, we were just, playing around it, right? But in here, we are going to make sure that we understand the meaning of the set, the finite set, and then look at some examples and know how we can deal with it. All right, so if we talk about a finite set, how do we understand a finite set, right? So basically, a finite set is a set with a limited number of what? Elements, right? If we talk about finite sets, it basically tells you that it's a set, right, that has a limited, right? It has a constraint, or it has been restricted to a certain number, or it has been restricted to certain range of what? Numbers, right? So let's look at the mathematical definition. So definition. So it's a set with a limited number of what? Elements. It's a set with a limited number of what? Elements. And that is what we called finite sets. Finite set. Right. So let's look at some examples. So as the name goes, finite set, we said it is a set with a limited number of what? Element, right? So we can talk about something like a set that contains an element or items 1, 2, 3, 4, 5, 6, right? So then we close the curly bracket. So it means it is limited up to what? 5 elements. So we say that our first example is going to be open curly brackets 1, 2, 3, 4, 5, close curly brackets, right? So this is a finite set because the last element is known. We know the last element, and that's why we are calling it a finite set. A finite set. All right. And the second example here is set of vowels. Set of vowels in the English alphabet. Set of vowels in the English alphabet. Set of vowels in the English alphabet. So we know the vowels in English alphabet, right? We know the A, we know the O, we know the U, right? We know all the vowels in English alphabet. They are limited. Even if we are to talk about the consonants, they are also limited, right? So we know that a set of vowels in the English alphabet is limited to a certain number. I think 5 or 6, right? So set of vowels in the English alphabet is a finite set. It's an example of a finite set. Great. This is so powerful, right? Now that we have been able to understand the concept of finite sets and we looked at some examples, now we can move on to what we call cardinality, right? Right? So we are going to look at what a cardinality is, right? So cardinality, right? So when we talk about cardinality, if let's say a set A has n elements, right? If a set, let's say A has n elements, then we can say that the cardinality of the set A is equal to what? N, right? So that is all we mean by cardinality. Right? So if a set A has n number of elements, then the cardinality of that particular set A is absolute of what? A is equal to what? N. That means the number of the set A is equal to what? N. N elements. So that is what we call cardinality. So if we talk about cardinality, it's all we refer to as that. Now, let's look at some examples of the cardinality. All right. So we look at an example of the cardinality is, let's say you have A equals curly bracket, open curly bracket, A, B, C, right? So if you are to find the cardinality of this set, then we say that the cardinality of this set is 3 because you have 1, 2, 3 elements. Great. So the cardinality here is 3. Great. So the cardinality is the number of items in the set. The number of items in the set. So we have 1, 2, 3. So 1, 2, 3 what? Elements. And that is the cardinality. So brilliant, right? So brilliant, right? So that is an example of a cardinality. Now, we have been able to understand the basics of the empty sets. We looked at some important observations. We looked at some examples. We looked at some differences, key differences between empty sets and a singleton set, right? So we have come far to look at the finite set, right? We looked at the finite set and we have given some examples. We have come back down to cardinality. We have given some example and I believe that we are cool with it. Now, let's move on to infinite sets, right? Infinite sets, and that is the last thing for the day. So we're going to look at infinite sets. So with infinite sets, it's going to contain a lot because that is where you see the equal sets, equivalent sets, and those many things, right? So we look at infinite sets. Infinite sets, right? So we have to define what an infinite set is, right? So we can copy the definition from here. We said that finite set is a set with what? A limited number of what? Elements. So infinite set will be the reverse, right? So we are going to say that definition, a set with unlimited, right? Or a set with infinitely many elements. We can say that a set with infinitely many elements. A set with infinitely many elements is called infinite set. As simple as that. A set with infinitely many elements is called infinite set. As simple as that. As simple as that. Don't stress yourself. Now, let's look at some examples of infinite sets. So, examples of infinite sets, we can talk about capital N, of which yesterday we mentioned of it, right? That is natural numbers, right? And then we can talk about Q, capital Q, which represents rational numbers. Then we can talk about Z, which represents integers, right? And then we can talk about the R, which represents real numbers. So when we talk about infinite set, it is a set with infinitely many elements. Infinitely many elements. It means we don't know the end, right? And a clear example is natural numbers. Can you give me the end of a natural number? No. A natural number goes to what? Infinity. You cannot give me the end of a rational number. It goes to infinity. Integers, same. Real numbers, we don't even talk about it, right? So these are examples of infinite sets. Now, let's look at the uses in what? Algebra. The uses of infinite sets in algebra, right? The uses of infinite sets in algebra. Right, so uses. So first of all, if you understand the concept of infinite sets, one, it will help you when it comes to sequences, right? Or sequence. Two, it will help you when it comes to domain of functions. And three, it will help you when it comes to number systems, right? So the first one, as I mentioned, is going to help you when it comes to sequence, right? Sequence. 2 is going to help you when it comes to domain of functions. Domain of functions. And then the third one is going to help you when it comes to number systems. Number systems. Right. So that is the uses of infinite sets in algebra. The use of infinite set in what? Algebra. It's going to help you to understand sequence. It's going to help you to understand domain of functions. It's going to help you to understand the number system. Right. So that is the few uses of the infinite sets. Right. Now that the infinite set has synced in, now let's go and pick equal set, right? So the next on the list is equal sets. Equal sets, right? So when we talk about equal set, we have to define it. We have to define equal set. I believe that this is an easy one to define, right? So when we talk about equal set is basically a set. We call a set an equal when we have two sets, right? Two sets are equal if they contain exactly the same element. If they contain exactly the same element. So we can only talk about equal set when you are talking about what? Two sets. And these two sets have what? Equal element. Exactly equal elements in the set. Right. So we say that two sets are equal. Two sets are equal if they contain exactly the same, if they contain exactly the same element. If they contain exactly the same element, right? So we talk about equal set when you have two sets, right? And that is where you talk about the sets having exactly the same element in the two sets, right? So let's say set A, set B. This set is the same, having the same element as what? The set B. And that is where you can talk about equal set. Equal set. Now, we are going to look at some key properties under the equal set, then we can move on to equivalent set, right? So, some key properties. So, key properties, right? When we talk about equal sets, we don't prioritize order, right? So in equal sets, order does not what? Matter. Order does not matter in what? Equal sets, right? So order does not matter. Order does not matter. Two, repetition does not matter as well. Then, yeah, so these are key properties that you have to know about what? Equal set. Two sets are equal if they contain exactly the same elements in their set. And so the key properties are order does not matter, repetition does not matter as well. So let's look at example. A perfect example is, let's say you have set A equals 1, 2, 3, right? This is set A, right? And let's say that set B is equal to 3, 2, 1, right? So these two sets, set A equals 1, 2, 3, set B is equal to 3, 2, 1, we say that these two sets are equal, right? Because they have the same or exactly the same what element. We have one here, we have one here, we have two here, we have two here, we have three here, we have three here. And the cardinality is the same. The cardinality here is what? 3. The cardinality here is also what? 3. So that satisfies the condition of what? Equal set. So that satisfies the condition of what? Equal set. So this implies that A is equal to what? B. Set A is equal to what? Set B. And that is the equal set. So if you understood this, then let's move on to equivalent set. Equivalent set. Equivalent set. So you're going to talk about equivalent set. Equivalent sets, right? So when we talk about equivalent sets, most times students misuse equivalent set and equal set, but I don't want you to misuse these two terms, right? So I'm going to explain that too explicitly as well, so that you don't misuse these two terms, right? So definition for equivalent set. Definition for equivalent set. So basically, if you are going to talk about equivalent set, in that instant as well, we are going to talk about two sets, right? So in equivalent set, we also have two sets. Two sets are equivalent, right? Two sets are equivalent if they have the same number of what? If they have the same number of what? Elements. So let me list some example for us to compare it to what? The equal set, right? So an example for equivalent set. An example for equivalent set is, let's say that you have set A equals 1, 2, 3, right? And set B is equal to A, B, C, right? So you can see that set A has the cardinality of set A is 3, right? Is 3. The cardinality of B is also 3 because we have A, B, C, of which is 3. 1, 2, 3, of which is 3. So 3 here, 3 here. That is called equivalent set. Equivalent set. So in equivalent set, we are not interested in the elements that are in the set. We are interested in the number. We are interested in the cardinality. The cardinality. So in equivalent set, what we want to see is that this set is having 3 elements. This set must also have what? 3 elements. Then cardinality is satisfied. But when it comes to equal set, if this set is having 3 elements and this set is also having 3 elements, and the element in this set is not the same as the element in this set, you don't qualify it to be what? Equal set. Let me come again. When you come to the equal set, let's say you have set A, you have 3 elements. Set B, you have 3 elements. But then, for it to be equal set, the element in set A must be the same element in what? Set B. So let's say you have 1, 2, 3. The set B must also be what? 1, 2, 3. The same element. But in the equivalent set, when you have 1, 2, 3 here, what we just want to see in set B is that it has the same number of what? Elements. That is the cardinality. So if 3 is here, we are making sure that 3 is here, and then cardinality is what? Satisfied. But in this case, we want to see vividly the same element in both what? Sets, with equal number of what? Elements. And that is called equal set. And this is called what? Equivalent set. I believe you are good with that. Thank you. So once you are good with that, then I can tell you that the equivalent set of these two elements is talking about the cardinality. So the cardinality of A is equal to the cardinality of what? B. That means the element in A is equal to the element in B, and that satisfies what? Equivalent set. Now, once we have been able to understand these two concepts, I don't want you to confuse this equivalent and equal set. So get it clear, all right? So now, what I want you to take note of is that equal set is never equal to equivalent sets. So let me write it with a red ink. Equals or equivalent set is not equal to equal set. Take note of this. Equivalent set is not equal to an equal set. An equivalent set is not equal to an equal set. Take note of it. It's very, very important. Now, once we have been able to understand this concept completely, now we can move on to what we call subset. Right? So we are going to look at subset. That is a 7th thing here, subset. Right? So we are going to look at what subset is, the definition of a subset, right? So when we talk about a subset, basically the basic definition in mathematics for subset is, let's say if you have a set A, right? A is a subset of what? Let's say B, then if every element of A belongs to what? B, right? So let's say A is a subset of what? B, that means that every element of what? A belongs to what? That of what? B. So let me write it. Definition. A is a subset of B if every element of A belongs to B, right? So if every element of A belongs to what? B, then we can talk about subset. So the notation is A subset B. So this is the notation. A is a subset of what? B. It means that if every element of A belongs to B, that is A is a subset of what? B. That is so interesting and so easy to what? Comprehend. So we're going to look at some example, then we move on. So example of a subset. Example. So our example is, let's say you have sets of 1 and 2. This is a subset of 1, 2, 3, right? So you see you have 1, 2, 3. This is a subset. This is a subset of what? This. Because the elements that can be obtained in this, the elements that are in this, they are all in this, right? All elements here are here. So this is a subset of what? This. So let me bring it to reality. So you were born out of your dad or your mom, right? So you are a subset of your parents. You are a subset of what? Your parent. Within your parents, you can be found, right? So you are within your parent, and that is a subset. So you are a subset of what? Your parents, and that is so understandable, right? Now let's look at some facts, right? Let's look at some facts in this. Let's look at some facts. So facts, right? So let's say that one, every set is a subset of itself, right? So that is the first fact. It's a fact that no one can doubt it, right? Two, empty sets is a subset of every set. Three, right? Yeah, so I think two is enough. This is valid, this is also valid. You know why? Every set is a subset of what? Itself. So if you take something like this, right? If you take something like this set 1, 2, set of 1 and 2, this set is a subset of what? Itself. This set is a subset of itself. And the second point is saying that empty set is a subset of what? Every set. So if you take this particular set, for instance, you have an empty set inside. So if you're asked to list all the elements or all the elements in this set, you can have empty sets, you can have 1 only, you can have 2 only, you can have 1 and 2, the set itself. So this is the set obtained from this small set, right? So every set, right? Every set is a subset of what? Itself. And every empty set is a subset of every set. So take note of these two facts. Proper subset. So proper subset. So we are going to look at proper subsets. Proper subsets. So basically, if we talk about proper subsets, then we are just talking about, let's say, a set, all right? A subset of, let's say, a subset of B is proper, right? Is proper if one is subset of what? B is sub or equal to B, and A is not equal to B, then we can say that that is what? A proper subset. So we write it properly as A sub what? B. So with the A proper subsets, there is no equal to under the what? The subset, right? So A subset B means that it is proper. So proper subset does not have what? Any equal to under the what? The subset. So A subset B, and this is the proper subset. So if you have A subset B and A is not equal to B, then we can say that A is a subset of B, and that is what we call the proper subset. Proper subset. Now, the next thing on the list is universal set. Universal set. So when we talk about universal set, you know that when it comes to the family level, let's bring it to our family, right? So we talk about your parents, right? Mother and father, they are the universal set of the family, right? So within your parent, you can see yourself, right? So they are the universal set, right? So universal, each one is universal sets, right? So definition, right? So a universal set is a set that contains all the element under consideration, right? So a set or the universal set the universal set contains all the elements under consideration. All the elements under consideration. So that is a universal set. Now let's look at some example. So example of a universal set is if we are discussing something like discussing real numbers, right? If you are discussing real numbers, right? If you are discussing real numbers, then we can say that universal set is equal to what? Real numbers. Because you know that real numbers contains all numbers, and we are saying that universal, right? Something universal means contains everything. So universal set is equal to what? Real numbers. If you are discussing what? Real numbers. Now, this universal set is used in complement of a set, right? Complement. 2, it is used in Venn diagrams. It is used in Venn diagrams. So these are where universal sets are being used. It is used in complement of a set. It is used in Venn diagrams, right? So that is where we use the universal set. All right, so now we move on to the next subtopic on the list is union of a set. Union, right? So we look at union. Right? So union represented as the same U, right? What is it about? What is it? So basically the union, okay, the union of, let's say, two or more sets, the union of two or more sets in an operation is if you have the union of two or more sets, then we can talk about union of a set, right? Union of a set. So perfect example is marriage couples, right? They are union. So marriage is a union of the husband and the wife, right? So union of these two people forms a marriage, right? So union, perfect example is marriage. Great. So that is union. So this basically means, or the meaning of this is one. It means that it means combining elements from sets, right? Combining element from sets. And that is all the union set means. So if you combine element from sets, then you can talk about union of a set. So let's look at this definition. So let's say that A and B be a subset. Let's say that A and B be a subset of the universal set U. Then the union of A and B denoted by A union B is defined by so we are going to write the algebraic definition, then we will use visual explanation or visually to explain it as well. So we say that A union B is equal to X belonging to U such that X belongs to A or X belongs to what? B. Or we can equally say that X such that X belongs to A or X belongs to what? B. So this is what? Algebraic representations. This is algebraic representations, right? So basically, we can equally use a diagram to represent this information. So we say that this right here, union, so this is A, we call this A, this is B, right? This is A, and this is B. The union of A and B will be this here, right? Because we are talking about union, right? So because we are talking about union, the union will be this section, and the common section. So we say that the union of A and B is represented in the diagram on the board. Now, let's look at the last part of it where we have the intersection. The second part of it, so let's say that the intersection of A and B denoted by A intersection B and defined by the sets A intersection B equals S is such that S belongs to A and X belongs to what? B, right? So you can see that when it comes to the union, we used or. When you see or, it means union, right? So if you see or, it means union. But if you see and, then it means intersection. So the word and is intersection, and the word or is union, right? So that is the simple thing you have to understand about that. So let's now put that in a diagram. Let's put that in a diagram. So we are going to have the intersection of A and B, the intersection of A and B. So let's say this is A, this is B. So the intersection of A and B, it means that the common element between A and B is going to be what? This section, right? So this is the intersection of A and B. The whole of this is A. The whole of this is B. And the common section between A and B is this section. Right? So that is the intersection of A and B. Now the next one is when we talk about the disjoints, right? So let's say that the subsets, right, of A and B are disjoint, right? The subset of A and B are disjoint if A intersection B is an empty set, right? So if A intersection B is an empty set, then we can have a disjoint set. We can have a disjoint set, right? So we can equally represent that in a diagram, right? So we are going to use the diagrammatic to explain that, right? So disjoint set is just this. So you have this set, you have set A and you have set B. Set A is disjoint from set B because they have no element in common. So this is A and this is B. So this is A intersection B, an empty set because they have no common what element, and this is what we call empty set or disjoint set, right? This is the disjoint set. That is so amazing, right? So that is basically what you have to know about this, right? Now let's look at some common mistakes that students do commit from the beginning, right? We are going to start from the beginning where we talked about finite set, infinite set, we talked about empty set, singleton, and those stuff. Let's look at some common mistakes that students can commit in their exams or whatever. So I'm going to use red ink to write that. So common students mistakes. Common student mistakes. So we have one. Students normally think that. So thinking that when you have a very large number or a very large set, then you have infinite. It is not true. If you have a very large number, it doesn't mean it is an infinite set. So take note. 2, sometimes we forget, right? So forgetting that a set with, right, condition, a set with conditions contains, a set with conditions can still be finite. A set with conditions can still be finite. And the third mistake that students can commit is that they can usually think that or they normally confusing finite sets with bounded interval. So these are the 3 mistakes that students normally commit in their daily exams lives, right? So don't commit these mistakes, all right, because you have known them. Now let's go to the importance of learning all these things. The importance, right? The importance of what we have learned in algebra, right? The importance of what we have learned in algebra, right? So the first one is like a preamble, understanding finite and infinite sets. Understanding finite and infinite sets helps in 1. It helps you in counting elements, right? It helps you in counting elements. So if you understand finite and infinite sets, it helps you in counting elements. That is 1. 2, it helps you to solve, so solving algebraic problems. 3, it helps you to understand, so understanding of domains, understanding domains of functions, and then finally it helps us to apply, so applying union and intersection correctly. It helps us to apply union and intersection of sets correctly. So that these are four importance that we will gain from learning those things that we learned from the beginning to the end in algebra. Now, I'm not going to leave you just like that, right? I'm going to give you a try work for you to try at your comfort zone, right? So, quick practice. Quick practice. 1. Our first practice problem is, I want to ask you, or I'm giving you that you should state whether a particular given set is finite or infinite, right? So state whether or not, state whether the following sets are finite or infinite, right? So the first one is x belongs to what? Z, such that -3 less than or equal to x less than or equal to 5. So that is the first problem. State whether the following sets are finite or infinite. So the first one is open curly bracket, s belongs to z such that -3 is less than or equal to x less than or equal to what? 5. That is the first problem. The second problem is that is the set s belonging to natural numbers such that x is even, such that s is even, finite or infinite. Finite or infinite. That is a question, right? So is the set open brackets s belonging to natural numbers such that s is even, right? Finite or infinite set. So these are your two practice problems. Please try it and leave your answer at the comment section. So conclusively, I'm going to give you the summary for what we have done for the day. So basically, in this particular episode, which is episode 2, we classified sets based on the number of elements, right, that they contain, right? So we classified the set based on the number of elements that they contain. 2, we learned that a finite set has a limited number of what? Elements, right? A finite set has a limited number of what? Elements. And we know that an infinite set has unlimited number of what? Elements, right? So we're looking at these two differences. The distinction is that the distinction is very, very important in algebra. You being able to differentiate between these two finite and infinite sets is very, very, very important in algebra. We are now ready to study how sets, right, combine and interact. Okay, we are now ready to study how sets combine and interact, right, which leads to, or which leads us naturally, right, it leads us naturally to the laws and the properties. It will lead us naturally to the laws and properties of union and intersection of sets, right? So this episode has been very fantastic, so interesting. It contains a lot, right? It contains a lot. But the next episode, which is going to help us to learn how the laws and the properties interact or engage in the union and intersection of sets, watch out. And that is going to be episode 3. Please don't forget to subscribe, share with your mates, comment. I really love that aspect. Comment and subscribe. And I really appreciate that aspect. Thank you very much for watching. See you next time. Bye bye.